Hello, my name's Eleanor Clapp. I'm an ECT2 teacher. In former lives, I've been a commercial property solicitor, a basket maker, primary school teaching assistant, and now I was a biology trainee but became a physics specialist thanks to the Ogden Trust last year. I cannot sing their praises high enough. STEM Learning, especially Alan Denton, and Physics Partners that got me to be able to teach the whole of A-level physics last year on my ECT 1 year due to our physics specialist leaving very suddenly. So talking to a whole load of people that have got lots more experience than me, I was like, what can I tell you? I can't really tell you anything, but I can share some really cool ideas. And I found myself using huge amounts of Play-Doh to teach science. And so I thought, well, I'll do some demoing. I like making stuff. Anyone who's got small kids knows that Play-Doh is fantastic. But what people don't know is it's really cheap and easy to make. And obviously teachers finding cheap resources and replaceable resources is really important. So I was going to do a demonstration. We're going to maybe, I don't try and show it somehow, but also I'm not sure if I can use my hands to demo stuff at the same time, but we'll see. So I've prepared a little PDF. Cool. Right, so I prepared a PDF that has all the details in. So I'll do it. Sorry, yeah, okay. So for Key Stage 3, biology, chemistry, physics, Play-Doh great. Genetic inheritance we're going to build atoms, build circuits. Key Stage 4, modelling enzymes you can do with Play-Doh. Mendelian inheritance, building hydrocarbons, isotopes, atomic structure.
At this point, the sound has disappeared. I'm carrying on telling you how you can do a really cool A-level practical in physics to find out Planck's constant using Play-Doh as a variable resistor. And I've got lots of pictures and ideas in my PDF that you can download following the QR code on the front or given the link. Play-Doh is really easy to make. You can use any of the ingredients that you just get from Tesco, so flour, salt, cream of tartar, you get that in the cooking ingredients aisle, a little bit of vegetable oil and gel food colouring. I've put the recipe on the sheet, but essentially it's a cup of flour, cup of water, half a cup of salt, tablespoon of oil, teaspoon of cream of tartar. Mix it together and use a microwavable bowl. 30 seconds in the microwave, mix, another 30 seconds to a minute, mix. It will look horrible and lumpy. Keep going, another 30 seconds to a minute, mix, and eventually it will come together to form a nice lump. Do a final 30 seconds and mix, and then you'll get something that looks like this one that I've made earlier, which is the quantity that you can make from a cup of flour and water. And so you can then start using it to make stuff. Pros and cons. Sometimes kids moan that it smells a bit funny. It's got gluten in it, so you might have gluten allergies to think about. It can sometimes make your hands a little bit crusty and sticky, so children might want to wash their hands afterwards. And it does tend to get a little bit played with and thrown around the floor, so you might lose bits gradually, but it's very replaceable and you can always make some more. It's very engaging material, so students that aren't often very engaged with practical work, you can give everyone a little bit of Play-Doh and everyone can be involved in the practical that you're trying to do. I think I'm talking here about when I did a little pressure practical with my Key Stage 3 students. Everyone had a little bit of Play-Doh and a safety pin, a drawing pin, and we looked at holding that Play-Doh, balancing on the tip of the pin and balancing it on the head of the pin, and then looking at the holes that it made and how much pressure was being exerted. And it was great because every child in the class had a bit of Play-Doh and a pin, and everyone could engage all at the same time, which made a really lesson that it worked really, really well. I've got lots and lots of ideas. I can't share them all at this time, so I've chosen to focus on maybe doing atoms and building atoms. So in Key Stage 3, you start looking at the periodic table and trying to work out whether students actually understand what the numbers on the periodic table actually mean? What's the big number? What's the small number? And Play-Doh lends itself really well to this. You probably want two colours, because you'll want one for your neutrons and then one for your protons or charged particles. I would suggest using the same colour for protons and neutrons, so it's clear that they've understood the difference between a mass number and a atomic number. So you can hand out different cards for different elements, and then you can get your students to count out and make the protons. Again, it doesn't have to be neat. So you're really just looking for understanding rather than a beautiful model. Some students love to make it beautiful, others it doesn't matter. So that's why it's nice and creative. I'm then counting up. So I've done the first 7 are protons, and then I've counted up from 7 to 14 to make my mass number, and then I can see instantly that I've actually got 7 neutrons as well. And you can then model to your children that the nucleus is actually a 3-dimensional thing. We draw it flat because it's easier to see it that way, but you can sort of use a lot of language. You can show them under a visualizer what you would like them to do. Then we're thinking about putting electrons, and again you can ask them, they can look at different atoms and see, do they know that the same number of electrons and protons are the right number. So that's your key stage 3. But moving on, you can use it again at key stage 4 when you're trying to start filling electron shells. And can they then show that you fill the right number of electrons in the right shells of the atom? 2 in the first, and obviously a maximum of 8 in the second. Then you can start introducing the concept of ions and getting a full outer shell. So we're gaining 3 electrons to complete a full outer shell, and obviously you can build this with different atoms, whether they lose or gain electrons. I then move on to show you can look at isotopes and what is the difference in the nucleus of isotopes. Well, I've built nitrogen 14, but what would nitrogen 15 look like? Well, we've still got the same number of protons, but it's the neutrons that changes number. What about nitrogen 13? What might that look like? Now I'm just making up numbers here, but it enables you to see, do your pupils understand what those different numbers are with models of Play-Doh? And you can go around and instantly see, do they understand, have they got the right numbers? And you can guide them very easily without having to there's no mistakes written in their books or anything at this stage. Then I move on to show how brilliant this is for modelling radioactive decay, which again is conceptually quite tricky. We're going to just pretend that nitrogen undergoes alpha decay, but we can then physically build an alpha particle with 2 protons and 2 neutrons. There's nothing magical about an alpha particle, it's just a helium nucleus, and you can show that there. And then you can physically move what you've got left to the other side of your equation and count it up. So you can count your protons, then you can work out what the element actually is, and then you can count your neutrons and work out your mass number. And you've essentially built a radioactive decay equation using your Play-Doh. It works really well for these sort of situations where something changes into something else. A process changes, you're adding and gaining electrons, or you're adding and gaining particles in radioactive decay. Then I'm modelling beta decay, and again this can be slightly conceptually tricky, but here we're taking a neutron and we're converting it into a proton and electron. So they're different colours, but because that's neutrally charged, I need 1 positive and 1 negative charged particle to balance out, and the mass is the same because your electron is tiny. So I can swap the neutron and put the proton and electron in the nucleus, but that electron doesn't want to be there. That electron is going to be shot out of the nucleus and becomes my beta particle. And it really shows that the beta particle is coming from the nucleus, and it's got a mass of 0. It's got a charge of -1, and therefore I can then count up my proton numbers, and I've now got 8 protons, and I can count up my neutrons and find the mass is the same. And I've built my equation, and I can check the numbers, but actually I've built it first and then model the numbers at the same time, and it can just really show that the beta particle comes from the nucleus, not one of the outer shell electrons. So Play-Doh is fantastic for modelling atoms and just being really clear to see whether your pupils have understood what is the atomic number, what is the mass number, what are electrons and how many go in the electron shells. So that was me demonstrating radioactive decay. The next brilliant thing you can do with Play-Doh is use it to build circuits, because Play-Doh, the salt and the water in the Play-Doh is a conductor, and it basically is a resistor, and you can build different size resistors. If you put a current through Play-Doh, you're essentially electrolyzing it. So anything you stick in that Play-Doh will start going crusty, just like your electrodes would. So if you're going to connect a battery, don't put any of your nice kit on there. Put little bits of foil or paper clips or anything that you can, that's semi-disposable. I'm also then talking about how LEDs are brilliant, because LEDs students are very familiar with. They're small, they're very cheap, but you do need a protective resistor with them, which sort of still sounds a bit scary. But if you just use them with Play-Doh, that is your protective resistor. So the Play-Doh acts as a holder for your LEDs, and then nobody ever needs to worry about resistors or anything else. They just act like little bulbs. So you get 2 little blobs of Play-Doh. You can connect your LEDs. Now make sure you've got one long tail. The long end needs to be pointing in the direction of the positive part of your battery. Otherwise it won't turn on, and you can then just make it light up. But you don't need anything clever. You just need a battery and some tin foil. So I'm just going to use some, just folding over little strips of tin foil now, just to show that it really don't need any clever equipment. So we're going to connect 2 in series. Make sure that you don't get a short circuit with your foil bits at the back, and you can see they glow up, but they're not as bright this time. The voltage, the potential difference is shared between the 2 bulbs, and they don't come on as brightly. And then you can do a third one and model series circuits, and the fact that because that potential difference is being shared, each light bulb doesn't get as much energy, and so it doesn't come on as brightly. And you'll get 3, you may not get 4, but you can see they're definitely dimmer. And you can use different coloured LEDs to make it look pretty. It doesn't matter too much. Holding on the battery like that is also really good, because it stops kids just keeping it permanently connected and winding down the battery. So from experience, if you plug stuff in, they'll leave it connected, and then you'll just find that you've electrolyzed your Play-Doh and got a flat battery. But if you just hold it and touch it to the foil circuits, it lasts longer. Here we are building a parallel circuit with 2 strips down. You sort of rearrange it, same number of bulbs, but you can get them all as bright, which shows that with parallel circuits you can get a much higher, well, each bulb has the same potential difference across. You can whap in loads and loads of different bulbs. They all come on lovely and bright, and it looks very, very pretty. Pack of LEDs like that, really cheap, about £5 from Amazon. They're semi-disposable, so everyone can have a go, everyone can take part. Again, it's really cheap stuff, and it isn't scary to use, and there's very little to go wrong. So it's great for Key Stage 3, introducing concepts at Key Stage 4 level. And again, there's a brilliant Key Stage 5 physics Planck's constant practical that uses the Play-Doh as a variable resistor with LEDs as well, which is brilliant. So Play-Doh, excellent stuff. Thank you very much.
Once on a video and showing them?
I tend to just do stuff under a visualizer live, because I think it's more impactful.
Yeah.
If you want to video it, just because you're not sure it's going to all go horribly wrong, and then by all means. But the nice thing about Play-Doh is you can do stuff live, and you can change it, and you can fiddle with it. And if someone's got a question, oh, but what about this? So you could say, yeah, do you want to do 92 pro? Yeah, fill your boots, go and do it. But do you think you're going to learn very much? You kind of get the learning from a small, yes, yeah. And we know that carbon and nitrogen don't undergo alpha decay, but it's really boring. By the time they've done 20 new protons, you go, do you really want to build uranium?
I said I've been the difficult kid in the past.
That's lovely. Thank you.
Thank you very much. The problem, of course,